Here we have the orbit of a star. The star is traveling in its orbit at 1,000,000 miles an hour. This particular orbit has 16 months in order to complete its revolution around its orbit. It's shining a light signal in all directions, but the observer is over here. So the light signal shining in this direction will be seen by the observer. According to Einstein and de Sitter, the light departs from this point at the speed of c, 300,000 kilometers per second, and disregards the fact that the star is moving in this direction at 1,000,000 miles an hour. When it's at this point here, it disregards the fact that it's moving in this direction at 1,000,000 miles an hour. At this point, it disregards the fact that the star is moving in this direction at 1,000,000 miles an hour. At this point, the star is no longer moving toward the observer, but it still sends the light at the speed of c, 300,000 kilometers a second. At this point, the star is moving away from the observer at 1,000,000 miles an hour, but the light disregards that motion and sends the light signal to the observer at 300,000 kilometers per second. At this point, the star is not moving towards or away from the observer. As the star speeds up and gets to this point here, the light will continue to move towards the observer at the speed of c, but disregards the fact that the star is moving at the speed of 1,000,000 miles an hour. I disagree with Einstein. I'm saying that the light leaving the star will travel toward the observer at the speed of c plus 1,000,000 miles an hour. Over here, the star is going this direction at 1,000,000 miles an hour. But that speed in this direction is added to the speed of light. The star's speed in the direction of the observer will only be 0.93 of 1,000,000 miles an hour. If this dimension is 5 and this dimension is 4.65, we divide 4.65 by 5 and we get 0.93. When the star gets to this point, it's moving in this direction at the speed of 1,000,000 miles an hour, but it's moving in this direction by the ratio of 3.35 divided by 5, so the light is moving in this direction at the speed of light plus 67% of 1,000,000 miles an hour. At this point, the star is moving 1,000,000 miles per hour in this direction, but it's only sending the light in this direction, the ratio of 2 divided by 5, which is 0.4. So the light is moving at the speed of light plus 0.4 of 1,000,000 miles an hour. At this point, the light is moving toward the observer at the speed of light without any adjustment for the speed of the star. At this point, we minus 0.4 of 1,000,000 miles an hour. At this point, minus 0.67 of 1,000,000 miles an hour. At this point, 0.93 of 1,000,000 miles an hour. And at this point, we minus 1,000,000 miles an hour. Now it begins receding more slowly. Over here, it recedes at 0.93 of 1,000,000 miles an hour. Over here, minus 0.67 of 1,000,000 miles an hour, minus 0.4 of 1,000,000 miles an hour, and over here it's not receding at all. As the star moves around, it increases its speed toward the observer, 0.4 of 1,000,000 miles an hour, 0.67 of 1,000,000 miles an hour, 0.93 of 1,000,000 miles an hour, and over here it's moving towards the observer at 1,000,000 miles an hour. If Einstein is correct, this is ahead of this, is ahead of this, is ahead of this. And so it's ahead by, let's say, that much. As we come around the curve, this is ahead of this, is ahead of this, all the way around to here. So we have the light moving towards the observer. If this is true, the starlight would represent the star sequence in orbit at any distance, in any direction. If Galileo was right, this is still ahead of this, but it's much faster. As we go this way, the light gets slower and slower. So this angle is much increased. It continues to skew more and more as the observer is greater and greater distances from the star. Now, when the light gets around to here, it's speeding up. We have to remember that this is going faster than this is going faster than this is faster, this is faster, this is faster, this is faster, and this is faster. So, in fact, over a great distance, this all catches up to this and passes it. And what we have is the light progressing like this. And as it goes further, it skews sharper and sharper and sharper and sharper. Bill Toole, a mathematician at New Paltz University, generously wrote out a mathematical formula describing how a star in orbit would look from a great distance away if light speed was constant with the star but relative for the observer, as Galileo and I expect. Using his formula, Bill Toole generated this graph on his computer. If we could see the starlight moving from the star to the observer from the side, it would look like this. From the receiver's viewpoint, it would look like this. This is a model of a 16-month cycle pressed into 3 seconds. At any moment in time, the single star would look like this. He also wrote a formula if light speed was constant without regard for the relative motion of the stars and the observer. Bill Toole, Einstein, and de Sitter expect the stars to look like this formula predicted. His formula generated this graph on his computer. If we could see the starlight moving from the stars to the observer from the side, it would look like this, based on the constant light formula. From the receiver's viewpoint, it would look like this. Bill Toole is the mathematician, and I'm taking his word on his formulas. His formulas do generate charts that correlate with my more elementary form of calculating star motion.